We are going to get started. So we are now moving into Unit 8. Um, I'm not extending any more due dates, so please make sure that you have checked the schedule um, and know when your assignments are due. Um, I updated the PowerPoints for Units 8 and 9. So make sure you use those updated PowerPoints. And in terms of what's going to be on the exam, generally go by what's in the PowerPoint. The content in the book is related to what's in the PowerPoints, but the PowerPoints are going to tell you things that you should be really studying for the exams and what we're going to cover. So we are moving into energy and reactions, Unit 8A. We're going to take a look again at potential and kinetic energy as it relates to reactions. We're going to identify chemical reactions as endothermic or exothermic, explain how the heats of reaction relate to the law of conservation of energy, determine enthalpy of reactions from graphical data, use stoichiometric relationships and the enthalpy of a reaction to calculate the total amount of heat consumed or produced. And we're going to look at enthalpy, entropy, and free energy to determine the spontaneity of a chemical reaction or process. We're going to do this unit as we did Unit 7B and just go straight through the PowerPoint and not separate out the questions from the content. So any questions that I show you today, they won't be posted on Top Hat. We'll do them together as a group. Let me open the chat because I'm not sure if Rihanna is in here. So I have everything open. Oh, you're here? Okay, cool.
Yeah. Hi, Dr. Graham.
Hey, all right. Okay, so let me move on. So the units that you should review for this content is heat and energy from Unit 2, ionic and covalent bonds from Unit 4, and chemical equations and stoichiometry of reactions that we just covered in 7B. So as I mentioned to you before, units like 1 through 6 are just like the basic things, the understandings that you need in order to get the higher level content. So now we've looked at chemical reactions, we've looked at the math for chemical reactions. Now we're going to take a look at why do reactions happen? And when reactions happen, what is the energy involved? So there's always going to be attractive forces between ions and atoms, and they are a form of potential energy that we have in chemical formulas. So we've already learned about kinetic and potential energy before, and we know that potential energy is stored energy. So the bonds between atoms or ions is that energy is potential. It's a type of potential energy. So before we get going, I want you all to take a couple of minutes, read through this question. Oh, write your answer down somewhere and we'll come back to it later. All right, so just a quick review for potential energy. Wait, sidebar. I realize when I do these recordings, I say, all right, so all the time. That's my segue into the next thing. All right, so anyway, and I have to cut those out when I'm editing these videos. Sorry, guys, I'm having a little ADD moment this morning. So potential energy is stored energy in terms of like water in a reservoir behind a dam, an automobile at the top of a hill that can coast down, the energy in a cold spring, and what's most important for us here is chemical bond energy. Kinetic energy is the energy of motion, and like water falling over a dam, the car actually rolling down the hill, and the spring uncoils and makes the hands on a clock move. Kinetic energy is also involved in the energy of molecules as they are moving when we increase the temperature on a substance, or if we add heat to a substance. So the laws of thermodynamics will help us to understand why some chemical reactions occur and others do not. So thermodynamics is the study of energy, work, and heat. And we can apply a thermodynamics to chemical changes, and the calculations that we would do determine the amount of heat obtained, let's say, from the combustion of a gallon of fuel oil. We can also apply thermodynamics to physical changes, and we've already done some of these calculations in which we determine the energy released by boiling water, or how much energy has to go into a certain sample of a liquid in order for it to go from one temperature to the next. So we did those type of calculations back in Unit 2. So when we're looking at chemical reactions or chemical, when we're looking at compounds, right, there is potential energy that is converted into heat when we form bonds between atoms or ions, right? So either bonds being formed or bonds being broken, there is either energy has to go into the system or it has to go out. And when I say system, that means what is exactly being involved. So if I'm talking about the amount of energy to go into breaking the bonds of the reactants, the system is just the reactants. When I'm talking about breaking bonds, right? And so we know that heat is the transfer of energy between two objects due to temperature differences. And the temperature is really just a measure of kinetic energy of the particles that make up molecules. And we can represent energy by big Q or little q. So what's happening in chemical bonds? Well, for chemical bonds, you have to put energy into breaking bonds. So when you have a reaction that's occurring, you have to break the bonds of the reactants. And in that process, energy has to be absorbed, or energy has to be put into those compounds to break those bonds, right? So we have to put energy in. When we are forming new bonds, right, energy is going to be released from that situation. So breaking bonds means that we have to add energy in. Forming bonds, energy is released when we reform those bonds. Now, for chemical reactions, the reaction is the whole thing, right? Breaking and forming bonds. So if the products have less potential energy than the reactants, then that means that the products are more stable. So if you think of the potential energy of compounds as the potential to react, right? The potential to react. If a substance has high potential energy, it has a high potential to react, right? And they want to react to become more stable. So most reactions are going to occur spontaneously when the reactants have more potential energy than the products, right? The products are in a state at which their bonds are so stable that they don't want to react. There's no need to react. So stable describes a substance that has little remaining potential energy and therefore a little tendency to undergo further change. So high potential energy, high potential to react. Low potential energy, low potential to react, and the bonds are stable, or the compound is stable. So this thermodynamics helps us to understand if a reaction will occur and how much energy or heat that's associated with the reaction. So the difference in the amount of potential energy contained in the reactants and the products will help us to determine if a reaction will occur. Do these reactants have high potential to react? And if so, what is the energy that's associated with the reaction? Rihanna, you cool on the chat over here?
Yep, looks good.
All right, so now that we've taken a look at what potential and what potential energy is in in the whole chemical reaction, let's now take a look at the bond dissociation energy, or the energy that must be applied to break a bond and separate atoms into isolated gaseous molecules. That's what bond dissociation energy is. And in that, we're going to take a look at identifying chemical reactions as either endothermic or exothermic, and explain how the heats of reaction relate to the law of conservation of energy. So, the strength of a covalent bond is measured by the bond dissociation energy. So I just mentioned before that bond dissociation energy is the amount of energy that you have to put into a substance in order for it to break those bonds. Bond dissociation energy, right? Energy needed to dissociate bonds, okay? The stability of a bond increases as that bond energy increases. So what does that say about bond dissociation energy? The energy that I have to put into the reaction. So how do we relate the bond dissociation energy to potential energy? What do you think is the relationship between the bond dissociation energy and the potential energy? Right, it's a direct relationship. So the stability of a bond, right, has to do with the potential energy. And as the potential energy increases, that means that I have to put in more energy to break that bond, right? So the more stable a molecule it is, the less reactive it is, right? So high total bond energy is more stable and less potential to react. Wait. So you guys said direct. It's not direct. The potential energy, right? So stability of a bond increases as the bond energy increases. So remember we said that bonds are stable when they have less potential to react, right? So so it's an opposite effect. So potential energy is low when the bond energy is high. Because why? I have to put a lot of energy into this molecule, right? So that means it has less potential to react, okay? So it's the opposite. So if I have high bond energy, I've got a more stable molecule and it has less potential energy to react. If I've got low bond energy, that means I don't have to put a lot of energy into breaking the bonds in this compound, then it has more potential to react. Yes, it's inverse. So low potential energy means stronger bonds, like Rihanna said. So it's the inverse reaction. Stability, high, low potential energy. High bond dissociation energy, low potential energy. So if we look here, notice that double and triple bonds have a higher bond dissociation energy. So let's look at the carbon-carbon bond with one single bond. The energy that is required to break that bond is 83 kilocalories per mole. However, a double bond, we need 147 kilocalories per mole, and a triple carbon-carbon bond is 201 calories per mole, right? It's like, imagine you and your friend were walking down the street holding hands, right? If you're holding one hand, it's easy for somebody to come and walk through you, right? But if you hold both hands, I know it would be weird walking down the street holding both hands, but it's a lot harder for someone to come and split the two of you apart when you're holding both hands, right? So the more bonds between two atoms, the more energy is required to break them. So would it be easier to, so would a triple bond have more potential to break than a double bond? Would that be yes or no? A triple bond, does it have high potential energy or low potential energy? Yes, low potential energy. So every chemical reaction involves the loss or gain of energy. And the units for energy, the SI unit is the joule. And most often you will see the energy involved in a reaction written as kilojoules, because the joule is kind of small in terms of the amount of energy that would be reacting. You will sometimes see kilocalories as well. So let's go back a slide. Notice that kilocalorie is a larger unit than kilojoules. Notice that 99 kilocalories, you have 413 kilojoules, right? So those values are generally looked at in kilojoules, but we can use both of them. So a chemical or a physical change, so the overall chemical or physical reaction that absorbs energy is called endothermic. Let's break up that little word. Let's break up the two words that we see in endothermic, right? Endo means what? What do you think endo means?
Outer.
Mm, into.
To absorb.
Yes, into. So endo
Observe
means
and
in, right? And thermic means what? If you see the little word therm, that always reminds you of what? Temperature or heat. Yes. So endo meaning in, energy goes in, right? So for an example, as a chemical process, it would be bond breaking, right? So this would be a chemical process, and ice melting would be a physical process, right? So heat is absorbed, and the Q value has a positive value, and it means that energy is gained, right? If a chemical or physical process releases heat, it is exothermic. So if endo means in, exo, what are some other words that you know have exo? You guys think
releasing out.
it means out, but anybody know of other words? Exoskeleton, right? External, right? So those words mean outside. Exit, yes, out, right? So energy is released in an exothermic. Now, remember, for every chemical process, we got to put energy in and energy comes out. We're talking about the overall reaction. Why? Because we have to put energy into breaking the bonds, and energy comes out of forming bonds. Just the difference between the two is either going to be endothermic or exothermic. So the chemical example would be bond formation, and water freezing is a physical process. So when the heat is released, the Q value is negative and energy is lost. So things like released, lost, expelled, those things let you know that energy has been released. Absorbed, gained, those are words that let you know that energy has been taken in. So if I have a reaction that's A to B, right? If I'm going in the forward direction from reactants to products, and I have a positive amount of energy in one direction, then the reverse of that reaction, B to A, is going to have negative energy, right? So if I go from A to B and I have an overall absorbance of energy, then going in the opposite direction from B to A, I'm going to actually release energy. Got it? All right, so quickly, let's do this one together. Bond formation is what? Write your answer in the chat. It's not on top hat. Cool. It's exothermic and it is going to release energy. All right. So what does the law of conservation of energy say? It says that energy can neither be created nor destroyed in any physical or chemical change. So the energy that goes in, right, and the energy that goes out has to be equal. The heat of it is very much the same as the law of conservation of mass, the conservation of energy. They are very similar. For a chemical reaction and even for a physical reaction, the heat of the reaction is the difference between the heat absorbed in breaking the bonds and the heat that's released in forming the bonds, right? So energy has to go in and energy has to come out. Now, some of that energy is directly involved in breaking and forming bonds, and the rest of it is either given off as heat, right? Given off to the environment as heat, or overall taking in as heat. So the heat of a reaction is called the enthalpy change, right? Change is delta, and the letter that represents enthalpy is H, capital H, not lowercase h, capital H. So I will say delta H whenever I'm talking about the heat of a reaction. And it is the overall total amount of heat that is absorbed or released during a reaction that takes place at constant pressure, right? The change of energy is going to occur when reactants interact with each other, right? So in order for a reaction to take place, the reactant particles have to bump into each other, and they have to bump into each other with enough energy for those bonds to break, right? The bonds have to break apart. So the reactants, they have to bump into each other. When they bump into each other, the bonds break in those reactants. And then the final step, the products are formed by new bonds, right? So the energy is changing in each of these steps. The molecules interacting with each other, right? There has to be a certain amount of energy in each particle before they hit each other. There has to be a certain amount of energy that goes in when they do bounce into each other for those bonds to break apart. And then the rearrangement of those atoms coming back together again is another step in which energy is involved. So delta H is the difference between the enthalpy of the products and the enthalpy of the reactants, right? So delta H is equal to the enthalpy of the products and the enthalpy of the reactants. We can relate also this enthalpy to potential energy. So when we look at diagrams, so we can say that the H of the products is the potential energy of the products, and the potential energy of the reactants. Okay? All right, so it's always going to be, the delta H is going to be the products minus the reactants. Oh, I already had it on the slide. Sorry. All right. So let's break this down a little bit more, because in some places you may be looking online or some other resources, they may have bond dissociation energy, right? So let's break this down. The enthalpy is the amount of energy released or absorbed during a process at constant pressure, right? If it's released, there's a negative sign. If it's absorbed, there's a positive sign. So the delta H is the change in enthalpy that results from a chemical reaction. Okay, so enthalpy is the amount of energy released or absorbed, and we can relate that to potential energy. And the enthalpy of a reaction is the delta H, which is the change in enthalpy that results from a whole reaction. So what we can say delta H is equal to is the potential energy of the product bonds minus the potential energy that is in the bonds of the reactants, right? So the energy of breaking the bonds is absorbed, which is why I have it blue, plus the energy of forming bonds, right? Which is energy that is released. Because if we think about it, the potential energy of the bonds and the products are being, so the energy of breaking bonds, this is related to our reactants, right? And the energy of forming bonds is related to our products, okay? So it goes in breaking the bonds plus the energy that is released when we form bonds. Go back to dissociation energy, right? Bond dissociation energy is the energy required to break a bond in the gas phase. And it also tells us the strength of a bond. These values occur at 0 degrees kelvins and at 1 mole. So it's based on 1 mole, right? And we know that if we have a strong bond, the potential energy is low. And if it's a weak bond, the potential energy is high, right? So you may see in some resources the heat of formation. So if there's bond dissociation energy, what do you think heat of formation is? It's the opposite. It's actually the energy that is either absorbed or released when bonds are being formed, right? The heat of formation. So what can we say? How can we represent this energy of breaking bonds plus the energy of forming bonds? If we think of going from reactants to products, we have the delta H of a reaction. So that can be written as the bond dissociation energy of our reactants. Remember, that's energy that's added in, so it's a positive value, plus the energy of the bond dissociation of our products. Why do I write it as negative? Because remember, we're not actually breaking the bonds in products, we're forming them. So bond dissociation energy is energy that goes in. So if we're talking about our products, the reverse is happening, so it's negative, right? So that ends up being our bond dissociation energy of our reactants minus the bond dissociation energy of our products. How else can we write this? We can write this as the heat of formation of our reactants. And remember, heat formation, the heat of formation is what's happening when we're forming bonds. So that would be a positive value, right? However, when we're breaking bonds, the heat of formation is the opposite. Just like when we're bond dissociation energy has to do with breaking bonds, the heat of formation has to do with building bonds. So that value would normally be positive, but because we're talking about reactants, it's negative. Plus the heat of formation of our products. We're going to make that positive because the heat of formation is a positive value. So what do we end up with? We end up with the heat of formation of our products minus the heat of formation of our reactants. And that's why delta H is going to be products minus reactants. Okay? So In some instances, you may see the information written this way, and that's why we end up with delta H of the reaction is delta is the heat of our products minus the heat of our reactants. Trust me, it takes a bit of time for you to wrap your mind around energy of reactions, right? So the heat of formation is going to be a positive value when we're talking about building bonds, and breaking bonds is going to be the opposite. Whereas the bond dissociation energy is going to be positive when we're thinking about the value itself, not in terms of exothermic or endothermic, but the idea is that that value, that physical property of a substance, given as its definition, bond dissociation energy, is going to be a positive value when we're talking actually about building bonds. Whereas if we're looking at the opposite, breaking bonds, then we would have to flip the value to be negative. I hope that understands. Just watch the video again later for it to make more sense.